All right, let's get started. As Chief Systems Engineer, my job is to architect the energy management system for our new micro EV. We're starting with a completely blank sheet of paper, and my first directive to the team is simple. Forget everything you think you know. The old playbook? It's obsolete. The rules of this game have fundamentally changed.
Okay, let's just get right to the point. This number right here, this is why the old playbook is now worthless. This is from a new Chinese regulation, and it sets a mandatory energy consumption limit. For my team, this isn't just some target. It's a hard line in the sand. You miss it, you're out. This one number officially makes the old way of building cheap, simple EVs a thing of the past.
So, to engineer a vehicle that can actually win in this new world, we need a disciplined, structured plan. This is our engineering roadmap for today. First, we'll dig into these new regulatory red lines. Then, we'll define our core architecture, dive deep into the software brands and the battery heart, and finally, we'll ground everything in the non-negotiables, safety and cost.
So, let's jump right in. Before my team even thinks about designing a single circuit, we have to deeply understand the boundaries we are being forced to operate within. And let me be clear, this isn't about choice. It's about market survival. I want you to pay very close attention to that one word, mandatory. You know, for years, standards like these were just recommendations, kind of like guidelines. Well, as of 2026, this Chinese standard is the law. If our car isn't efficient enough, it simply will not be sold. Period. End of story.
You have to understand, this isn't some minor tweak they're asking for. This regulation forces an immediate and pretty significant leap in engineering. The current leader in this market, the Wuling Mini EV, suddenly needs an 11% boost in efficiency just to stay on the road. So our engineering spec has to demand smarter, more efficient systems, not just cheaper ones.
And this is where the complexity really scales up. See, we're not just designing for one market, we're creating a global platform. And that means we have to navigate this whole matrix of strict, often conflicting rules, from Europe's L-category speed limiters and America's LSEV regulations, all the way to Japan's unbelievably tough efficiency benchmarks.
Okay, with the rules of the game set, my team now faces its first truly critical design choice. This is a foundational decision. Get it right, and we have a path to success. Get it wrong, and it's going to cascade problems through every other system in the vehicle.
This is a classic engineering trade-off. A low-voltage system seems safer on the surface, right? But to get the power we need, you have to pump a huge amount of current through the wires. That means thick, heavy, expensive copper cables and a ton of wasted heat. And wasted heat is the absolute enemy of efficiency. So, for our project, the decision is clear. It's really non-negotiable. To even have a chance of winning the efficiency game that these new regulations have created, we must adopt a high-voltage system. The physics of heat loss, plus the mature supply chain, makes this the only logical path forward.
Great, we've locked in our hardware foundation. Now let's move to the intelligence layer. This is where the real gains are made. The software strategy is what will ultimately make or break our efficiency target.
Now, we're going to give the driver choices, of course, but each mode is really a carefully crafted efficiency strategy. In our engineering requirements, for example, we're mandating an S-shaped pedal map for eco mode. This gently smooths out acceleration, nudging the driver toward a more efficient style, and they won't even notice it's happening.
Now, this is a key insight that a lot of engineers actually miss. Sometimes the most efficient thing to do is nothing at all. See, the physics of converting energy from motion back to the battery and back to motion again means you always have losses. So at highway speeds, it's way more efficient to just let the car coast than it is to regenerate energy you're just going to use again 2 seconds later. Our system has to be smart enough to know when to coast.
Okay, let's move to the heart of the vehicle, the battery. To hit our really aggressive cost targets, we're using lithium iron phosphate, or LFP cells. They're fantastic on price, but they come with a huge challenge for our software and for our ability to give the driver a range estimate they can actually trust.
Think of it like this. Imagine a fuel gauge that reads full from 95% charge all the way down to about 15%, and then suddenly, with no warning, it plummets to empty. That's what the LFP voltage curve is like. A simple voltage reading is basically useless. We need a much smarter system.
The solution, which we'll mandate in our requirements, is an algorithm called an extended Kalman filter. It's a brilliant piece of software. Basically, it runs a digital twin, a simulation of the battery. It predicts what the voltage should be, then it looks at the real measurement, and it uses the difference to constantly correct itself.
The result is a highly accurate state of charge, with less than 5% error.
The battery management system also acts as the battery's guardian, and you can see here it has to enforce some really strict, non-negotiable rules to prevent permanent damage when charging in the cold. Below freezing, charging is absolutely forbidden until those cells are warmed up. This is critical for battery life and for the overall safety of the vehicle.
So, we've designed a brilliant, efficient system on paper, but it's totally worthless if it can't be built on time, on budget, and above all, safely. This is where engineering has to meet the hard reality of production.
To handle the critical risk of unintended acceleration, we're implementing a simple but really robust safety architecture. We have a powerful main controller doing the complex math, but we have a separate, low-cost monitor chip that's basically a watchdog. It independently reads the pedal and constantly checks the main controller's work. If they ever disagree, the simple chip always wins. It just cuts the power.
And this slide really lays it all bare. The razor-thin margins we're working with. This is our target bill of materials. The entire high-voltage powertrain and battery system, the heart, the brains, the muscle of the car, it has to be delivered for roughly $2,000. Every single component choice has to be scrutinized against this budget.
And this brings us to the most critical takeaway from this whole exercise. After we've squeezed every last penny from the hardware and the supply chain, the physical components have a fixed cost and a fixed performance ceiling. That final, critical 10% of efficiency, the part that actually gets us across that regulatory red line, it's created entirely by software.
Which really leaves us with a provocative thought as our whole industry reinvents itself. In this new race for efficiency, is the next great automotive engineer actually a coder? Thank you for joining me for this engineering deep dive.